Hello, David Paul here. Right, where am I? I'm at the University of Coimbra in central Portugal, and this is the capital city of the province of Coimbra, where I've got my house. So you'll be seeing some videos about the house later on, but today I'm spending a day in Coimbra having a look at some things that I wanted to see for ages. I've been planning this for a year, and it's like kind of like a dream, you know. It's like bursting out of a dream and finding it's actually real. But anyway, this is the University of Coimbra, very famous university, founded in 15 something or other. It's very, very old. I think it was set up by King Alfonso. But anyway, the the bit that excites me, because you know I'm a physics teacher, is this thing: Departamento de Física. So that's the physics department, which would be mine, you know, my kind of place. So let's go in and have a look, because I got something on display. Everybody should have one of these. It should be a law, you know, you've got to have one of these. So what is this? This is called a Foucault pendulum, named after Jean Foucault, Frenchman, who invented it. What is it? Well, it's a pendulum, but it never stops swinging, because there's a switch at the top there which gives it a little electrical impulse, which attracts it to the sides. Usually it works by having magnets at the side, and it gives it a little impulse to overcome the air resistance, so it never ever slows down. It just keeps swinging forever, as long as you've got the electricity switched on. So what this thing does, it's free to rotate at the axis at the very top there. So there's no restriction on it. It's not like a piece of string where it's restrained and it couldn't turn around. So it can just swing in any orientation that it wants. And if it's on the, if you were to position this on top of the North Pole, not the magnetic pole, but the point of rotation of the axis of the Earth, you would find that this thing just moved slowly around this compass here and executed a turn in one day of 360 degrees all the way around, and it would just perfectly carry on doing that, well, forever, or until the Earth slowed down or something. So it would just carry on doing that. And at the opposite extreme, if you were to take this and set it at the equator, all it would do is just swing up and down with regard to the equator, sort of crossing it, and it wouldn't go in any direction at all. It would just go back and forwards across the compass and maintain the same position. And then at positions in between the two, it executes different sorts of rotation. It doesn't rotate totally, and it doesn't stop totally either. I can't remember quite how it goes. I think it has a particular angle associated to the latitude that it's at. So it sort of goes in a kind of a pair of triangles like that, and that's about it. That's all it does. And from that you can determine what latitude you're at by just measuring it if you want. It's a bit of a faff around sort of method in these days of GPS, but it's an amazing piece of physics, and it's just neat, you know. It has a certain beauty to it. So I'm going to show you the chart which explains how it works. I'm going to have a go at translating Portuguese as well. Okay, let's get the words in. So there's the North Pole there, here, and here, and as you can see, the picture underneath the line of oscillation is changing. It's rotating, but the line of oscillation is not. It's just up and down all the time. As it says here, o plano de oscilação do pêndulo visto por observador na Terra, which means a plan of the oscillation of the pendulum from a viewer for a viewer for the viewer observing on the Earth, right? So he's observing on the Earth, and that's all he sees. He sees that the pendulum's moving, which is like this. He thinks that the pendulum's moving around, whereas in fact the pendulum's not moving at all. The Earth is moving beneath it, and that's that. And it has relevance for a lot of things, a lot of physical effects. This thing here called the Coriolis effect. Different rotations of storms in the north and southern hemisphere. So if you're in Britain, where most of the people watch my videos, they're rotating, I think, in the clockwise. No, that's the southern hemisphere, so it's going in that direction for the northern hemisphere, anti-clockwise, and in the southern hemisphere it's going in the clockwise direction. And if you were to go to the equator and pull a plug out in a sink, you'll find that the water just goes straight down. And funny enough, this effect tails off towards just going straight down the hole exactly at the equator. When I'm in the Philippines, I do notice that you pull the plug out and the water kind of goes rather straight when it goes down the hole. And sure enough, at the latitude where I'm from, of about 45 degrees north, it goes down in the direction for the north, which is this anti-clockwise direction. Now, I haven't actually seen it happen, but I trust that it will go in the opposite direction when I ever go down to Australia or somewhere like that. So that's how that works. And it's quite spooky to look at. I've seen experiments where people have walked either side of the equator, and sure enough, it does actually change just over that short distance. So there you go. One last look at Foucault's pendulum. There you go. So, my first day in Portugal, and the first place I'm visiting, University of Coimbra, Physics Department. Thanks for listening. Muito obrigado.